Hello, and welcome to this OpenTopography tutorial. Today, I'm going to demonstrate how to conduct 3D topographic differencing of point cloud topography in Matlab. But first, I'm going to go over several slides on background information for 3D topographic differencing. So here are what the results of 3D topographic differencing typically look like. This is for the 2016 magnitude 7 Kumamoto earthquake, which occurred in southwestern Japan. So 3D topographic differencing produces a displacement field, which is shown here. The arrows represent the horizontal displacements, along with the pink circle, which is the error ellipse. And then the vertical displacements are represented by the color circle with the color bar shown here. So 3D topographic differencing produces this very, very dense array of displacements that, along with the error ellipse, look very similar to GPS displacements. Here are some good references that I recommend that you check out to learn more about 3D differencing. So how does 3D topographic differencing work? Well, we use the iterative closest point algorithm to align windowed subsets of point cloud data. So we start with the point cloud data set that was collected before the event. This is called the pre, or more technical language, the compare data set. And we also start with the data set collected post-event, or also called the reference data set. And the idea is to first take windowed subsets of both of these data sets. So for example, here you can see in blue the compare or pre-earthquake data, and this window size is typically a few tens of meters. And then the reference data set, we take a slightly larger window of that. The idea is that we can align the pre and post data set, and so we need that area that the reference data set is bigger to ensure that when we move the compare data set to try to align it with the post, that those two data sets can be aligned. And so here is an example of what the ICP algorithm is doing. So here you can see that the blue or pre-data set is iteratively moved closer to the red or post-earthquake data set. And at each of those steps, this is counting the number of iterations. And so here we see that around 15 iterations is sufficient to ideally align those two data sets. And then the alignment that is used is, the net alignment is that 3D displacement. We can also represent this mathematically. So most ICP algorithms use a rigid body transformation. So this includes a rotation and translation, but no shear. And so here is what that equation looks like. So we take that undeformed point cloud, apply a rotation and translation, but again, no shearing. And this then generates the deformed point cloud. So the next step is to get point cloud topography data that you can use for differencing. You may already have higher resolution topography data sets available, but if not, you can go to opentopography.org and use data sets that we host for topographic differencing. So you'll first go to OpenTopography's homepage, and then you will click Data to see all the data sets that we host. So you'll then want to zoom in to southwestern Japan, where you'll find the data sets that I use to generate the differencing results shown for Kumamoto in the presentation. Zoom all the way in, and here you can see that there's these two polygons indicating two data sets. So I'll come up here to select a region, and I'll put a box over a small portion of the earthquake area. So this shows that there's two data sets. There's a pre-earthquake data set and a post-earthquake data set. Now, if I want to ensure that I have the same box for both data sets, I can come over here to point cloud and right click, and that will then open up the job page with that same box that I had covering that I drew last slide. So it's typically best if you just set the default options. For topographic differencing, in this case, it's quite important that we keep the ground and unclassified dataset classifications and vegetation as well. So in this case, we only use the ground. We would go from 14 million to about 200,000 points. And that's just really not enough to do topographic differencing. So for this case, we're going to use both the ground, unclassified, and vegetation. Generally, in topographic differencing, if there's more points that are just ground, you would want to explore doing topographic differencing with just those ground points. But in this case, we're going to use the full point cloud topography dataset. Second option is point cloud data download. And so here you have the options of downloading the point cloud in a compressed LAZ or a compressed LAS file, or a non-compressed LAS file. And so in this case, I'm going to download, we have interest in looking at the LAS file, which is more compatible with different types of software. And then I will leave the rest of the options unchanged. So here's my email address. So feel free to enter your email address, and then you'll get an email when your job has finished processing. So this is looking at the pre-earthquake data. So it's helpful to put a descriptive title. So pre-earthquake for 3D differencing. And then I'll say submit. So this is now going to run on OpenTopography's servers at the San Diego Supercomputer Center. I'll then want to do a similar step with the post-Kumamoto earthquake lidar. Important, like we did for the post-earthquake data set, we want to use the full set of classifications. And the only option that I will want to change again here is to produce that LAS, so that non-compressed point cloud file. Scroll down, and I'll also add in a descriptive title here. So post earthquake for 3D. So then press submit, and again, like that first data set is being processed at the San Diego Supercomputer Center. So while those are processing, you'll want to then go to MathWorks File Exchange and use your email and password to log in, assuming you have a MathWorks account, and then you want to download 2 sets of code to use for 3D differencing. The first is last data, and this is a file that will let you open LAS and LAZ files in Matlab. And then the second is this iterative closest point, which is a very important part of this demo. And so that will give you the code ICP. Importantly, you also want to check that your version of Matlab has the statistics and machine learning toolbox. You can do this tutorial without that, but you will get better ICP results if you download that toolbox. So we'll now look at the topography data sets that we processed. So this is looking at that pre-earthquake data set processed on OpenTopography, about 160 seconds. And so here we have the point cloud results, so that points.las file. So you want to download this and name it something more intelligent, such as pre.las. You can also download the raster data set, which is interesting, and for example, could be used for vertical differencing, but that's not part of the demo today. And just for reference, here is what the point cloud, the raster generated from the full point cloud data set. And then here are the results for the post-earthquake dataset. So the dataset is larger. It's typically the case for later data. And this took about 240 seconds to process. And again, here we see that points.las file. So you want to download that and then also name it something more intelligent, such as post.las. You will also want to go to GitHub, where you can download the Matlab script that I developed for 3D topographic differencing for this demo. So you're going to go to my GitHub page and then download the ICP TopoDiff Matlab area, and then come down and download this differencing _ Matlab. Generally, here on this GitHub page, you can also find links for the Matlab file exchange documents, as well as those pre-computed LAS files for the topographic differencing. So we want to open up a Matlab and then direct Matlab to the working directory where you saved all your files. And so Matlab already automatically opened here to TopoDiff demo, but otherwise you can put the correct path in here. So then you'll want to go to the area where you've saved everything. And again, note we have the pre.las and the post.las files, and then this differencing _ Matlab, which you can download from GitHub, and then the Matlab file exchange files here are the ICP, and then the last data is inside the directory called last data. So you'll want to open up differencing Matlab, which I already have here. And we'll just go over what is in this Matlab script. So first thing to do is to clear and close all clear the variables and close all windows. And then I add the path to direct Matlab into the last data directory so that it can read the LAS point cloud files. So the next step is to tell Matlab some information about what you would like to do in the processing. So first we're going to tell Matlab the name of the pre-earthquake point cloud file. That's pre-dir. The file is called pre.las, and the same thing for the post-earthquake file. And then SZ here, that's the window size. So that's the resolution of the compare data set that's used in the differencing. So 50 is a very good guess for most input data sets. GRD, that's that grid spacing between areas where you estimate the displacement. Ideally, if you have sufficient time, SZ should be equal to, or perhaps even half of the differencing window size. But today, so this finishes efficiently, we're going to set GRD equal to 200. And this margin is the additional dimension of the post-earthquake window. So it needs to be just a little bit larger than the expected displacement in the earthquake so that the pre-earthquake file will align with the full post-earthquake file following that displacement. And so I'll talk through the rest of the file, but you don't need to change anything below now. So the first step is to then, in the code, is to read in the pre and post earthquake point cloud data. And then the second line extracts the point cloud data so that we end up with a pre-X, pre-Y, and pre-Z, which collectively are the point cloud data in the X, Y, and Z positions, and the same with the post-earthquake data. Next is to construct the set of core points used for the differencing. So the core points are the center of each of the windows that are used for differencing. So at each core point, we essentially have a measurement of that 3D displacement. So I use Matlab's command mesh grid to generate the core points, and then that generates a two-dimensional data set. But in the end, I just want it to be a column vector. So in the second line here, I flatten those data. So then we enter the ICP loop here. So we're going to go through each of the core points and estimate the 3D displacements. And so we're looking at this first line is we're extracting the X and Y coordinate of the ith core point. And then in this next set of commands, we are selecting the points that surround that core point. So again, we're extracting that window of point cloud topography that we're going to use in the topographic differencing. In this next block of code, we are going to shift those windows of the pre and post earthquake data set so that the window of the data set lies at 0, 0, 0. And the reason we do that is that we need that rotation to be relative to the center of the box and not somewhere halfway around the planet. And so here in this first line, I'm finding the mean of that pre-earthquake window, and then I subtract that mean in X, Y, Z dimensions from each of the point cloud data sets. Then the next big part, so the exciting part, this is where we do the 3D ICP differencing. Ultimately, here is the command. So we have the pre-trans and the Q-trans, and that is the pre and post windowed subsets of the topography. Again, with that shift, so that the center of those windows is at 0, 0, 0. And then this part here says that we want to minimize the point to plane distance. So your other option is to minimize the point to point distance. And for most applications, especially in the earth sciences, this minimizing the point to plane distance will yield higher quality results. So ideally, that's what you would set up. Now, if you don't have that statistics and machine learning toolbox, then you'll have to have the point option here. So that code would look like this. And for this demo, you'll get decent looking results. But if you're interested in using this for research applications, I strongly suggest that you install that better toolbox. And so then here is the output that you'll get from the ICP. So you'll get the rotation, the displacement, the RMS error after each iteration, and then the calculation of time per iteration. And then the results are stored here. And so in particular, that's the X, Y, and then displacement vector. And then when this all runs, the MATLAB script will plot the results shown here. So let's give this a try. So on my computer, MATLAB took about 6 minutes to run, and then these results popped up. So this is looking at the ICP displacements, The arrows are the horizontal displacements, and the colored circles are the vertical displacements. And so this earthquake had a combined right lateral motion as well as normal motion, and that is shown here. Where along this approximate line, we see a sharp change in the displacement signal, so that suggests that the fault is in approximately this area. And in particular, we see that this displacement here is approximately to the northeast, and this displacement here is reflecting motion towards the southwest. And so this is indicative of right lateral horizontal motion along a northeast southwest striking fault. In addition, we see that this area here towards the northwest moves down relative to this area in the southeast. And this is indicative of the normal motion that occurred during the earthquake.